Okay, I hope I'm audible and the screen is visible. So let us start. Welcome to the extra live session of this discussion session for the NPTEL course Quantum Chemistry of Atoms and Molecules. Today is actually I'm taking an extra class for 2 hours, and this is going to be the last discussion session for this course. I'm very sorry for this. One second. Okay, let us come back. Yeah. Anyway, so what I was saying that today is the last class, and uh, today I'm planning to solve some more numerical questions along with the assignment 12 solution. So without wasting any time, let us start. So I hope this will be an interactive session. You can ask me any doubt you have regarding whatever you have learned so far, or you have any doubt. I'll try to answer them to best of my capability. If I am not able to answer that, I'll share the answer maybe might be later with you on the comment section or in the discussion forum for the NPTEL uh, discussion forum what you have. And okay, let us start with the assignment 12 solution. So the first question is means this is actually a paragraph kind of a question which has three questions. So let us first read out the question. That the question is based on the ionization energy and mostly on the MOT, molecular orbital theory. And the question says that ionization energies of an atom A is 13 electron volt and another atom B has two kind of ionization energy, that is 15 electron volt and 20 electron volt. Now for the molecule AB, three ionization energies are also 12.8, 15 electron volt and 20.2, and uh, so and also it is given that there are four valential electrons are present in the AB. Now there are three questions are there, but before going to the questions, let us understand what has been given in the what data has been given to us. So there are two atoms are there, A and B. So first, let me make it plain. Yes. So and whenever you do this, I prefer to draw the energy scale as fast energy. So we have two kind of atoms. One is A, okay, which has um, its ionization energy is given here, right? That is 13 electron volt. Okay, and for B, there are two ionization energies. So ionization energy means how much energy is required to push one electron from the outermost valence orbital to the outside the atom in a gaseous state. I'm not going into the mm, definition, but that's what we are trying to say, that how much energy is required. So for A, 13 electron volt is required to push one electron outside the atom from the valence shell. And for B, there are two kind of energy. So one is at 15 electron volt, so obviously a little lower. So this orbital is one of the, say B1 is a little lower, and that is your 15 electron volt, and there is another which is B2 suppose, which has suppose 20 electron volt. I'm not sure why today my this screen is, why it is jumping so much. Anyway, so this is 20 electron volt. So this is the atomic orbital. So this is the orbitals, individual atomic orbitals are here. For A, it is a little higher than the B1 and B2. So this we have drawn from the whatever is given from the questions, right? So for A, it is 13 electron volt, and for B, it is 15 electron volt and 20 electron volt. Now, if we if this atomic orbitals forms molecular orbital, then it is saying that for molecule AB, three ionization energies are observed. Means one at 12.8. So it is little higher than this, obviously, right? Because then it will be 12.8. Another is exactly same as 15 electron volt. So it will be exactly same as B1, right? And another is a little bit lower than B2 because it's 20.2, right? Like here. So these are the molecular orbitals. Okay. Now it is also given there are four valence shell electrons are there. So if I have to fill up the electrons with a different color, let me choose this color. So there are four electrons. Right? So two here and two will be here according to the energy rule, right? So lower will fill first and then this. So, and then there is no electron here. So you can see actually if I have to talk about this is actually a anti-bonding orbital for A and B. If I have to draw this so like this and this is going to be so if A and B2 between A and B2 there is a linear combination you think one is a bonding kind of an interaction another is an anti-bonding kind of interaction then the bonding interaction is closer to B2 and anti-bonding interaction is closer to A1 in terms of energy, right? And another orbital, another molecular orbital is there which is exactly in the same energy of B1. Okay, so that is actually so if this is a bonding orbital BMO, so this is the anti-bonding anti-bonding MO, and then this is a non-bonding orbital. Okay, NB because it is not participating, so it is actually a lone pair on the B. So let us now we have drawn the system and molecular orbital picture actually we have drawn nicely. Now we will be able to answer the three questions what are being given. So first question is one. Yogita, are you there?
Yes sir.
So is this clear till now?
What?
Uh,
एक बार और बोलिए सर, नहीं समझ में आया.
ओके सो ओके आपको ये समझ में आया कि मैं द क्वेश्चन इज गिवन दैट देयर आर टू एटम्स ए एंड बी राइट
Yes
two
sir.
atoms are given for the first one the ionization energy is given 13 electron volt and for
Yes
B
sir.
दो ionization energy दिया हुआ है one is 15 electron volt another is 20 electron volt ओके इसका मतलब है कि बी के पास दो ऑर्बिटल है जहां से हम इलेक्ट्रॉन को actually we can ionize it to two conditions. But so it means there are two orbitals are there B1 and B2. One एक के पास है 15 इलेक्ट्रॉन एक का आयनाइजेशन एनर्जी है 15 इलेक्ट्रॉन वोल्ट और दूसरे का है 20 इलेक्ट्रॉन वोल्ट और उस हिसाब से हमने ड्रॉ किया ऐसे कि ए B1 एंड B2 आर फॉलिंग इनटू दिस काइंड ऑफ एनर्जी डायग्राम्स ओके एंड अगर
जी
ए और
सर.
बी मिलके molecular orbitals they form molecular orbitals then their molecular orbitals will look like this and this is also based on the ionization energy given in the question that one has 12.8 so actually this anti-bonding has this 12.8 electron volt so I'll in bracket I'll write 12.8 now this has 15 electron volt the non-bonding MO, and bonding MO has 20.2. So they are actually closer to the BMO is closer to the B2. Now the question states that among these four statements, which is going to be correct? So the first is the bond is more polarized towards A, or the bond is more polarized towards B. So as this is a heteroatomic molecule, AB is going to be a heteroatomic molecule. It is not like oxygen, nitrogen, O2, N2 like thing, where those are homoatomic molecules. But in this case, A and B have different energetics. So this is a heteroatomic molecule. You can look at the MO also. They have different energies. So what happened in this kind of molecules, that the uh, bonding orbital or the anti-bonding orbital, they have different kind of contribution from the different orbitals. So it depends on their nature. So here in this case, the bonding molecular orbital have much higher means similar nature towards the B atom, not A. But in case of antibonding molecular orbital, which is closer to the A orbital, or valence orbital of A, so that's why the antibonding orbital has much of the nature similar to A orbital. Okay. So actually here the bond is, that is why the bond is polarized to what's B, because we are talking about the bonding molecular orbital bonding, right? So bond is actually more polarized towards B because it is closer to B. Now, as I told you that there is a lone pair or non-bonding orbital is also there, and you can see it is lying at the same energetics as the B1. So actually the lone pair is on the B atom. So this is also correct. So first change the color. So obviously this is one of the correct answer, and lone pair is on B, not on A. So this is we are learning from there. Now, what is the bond order? The second question says that the bond order in AB is what? So if you can see bond order, so what is bond order? Bond order is number of electrons in the uh, number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. So if I have to do that, you can see that number of bonding molecular orbital is 2 electrons, 2. But in anti-bonding molecular orbital, there are no electrons. Why? Because it is already given that there are only 4 valence shell electrons are there. So 4 already being occupied, 2 in BMO, 2 in non-bonding orbital. So there are none in ABMO. So obviously, this is 2 minus 0 divided by 2. So that is 1. So the bond order is 1. Now the next question, that AB forms coordination complex with a metal ion. In this case, so this actually question is a little specialized question. If you have to look at you have to think of AB as a carbon monoxide. So CO. C being A, or two different. It is carbon monoxide is also a heteroatomic molecule, right? Diatomic, but two atoms are different. So in case of carbon monoxide, actually it acts as a ligand, and when in the some coordination complexes, when it forms bond with metal ions, so then you will see that the anti-bonding molecular orbital is empty. So the tendency of it would be that to get some electron from the metal. So actually your A is will be acting as a pi acceptor, and as B is filled, BMO is filled, so your so instead of A and B, so actually what does it mean that as the energetics of the antibonding is, as I'm speaking, I'm telling this multiple times, the energetics of antibonding molecular orbital is close to A, and bonding molecular orbital is close to B. That's why we can say that the bonding molecular orbital is over atom B, and the antibonding orbital is hovering around the, I should not say hovering, it's on A. Now, if that is the case, then A is acting as a pi acceptor, so it can accept electron because the antibonding molecular orbital is empty, and B is acting as a uh, so B is as a sigma donor. So B can donate electron and A can accept electron. So from this, so we can learn about the, so ionization energy can be recorded using the photoelectric effect, using the photoelectric effect, that is also known as the, I think the measurement process is known as XPS, or for, I guess that is known as XPS, photoelectronic spectra, X-ray photoelectronic spectra. From that, there you can get the ionization energy. So, and I hope this portion is clear. So I will go to the question number 4 and 5. So in delocalized MOT, MOT means the molecular orbital theory, which or among which this is going to be true. Actually, in delocalized MOT, unhybridized orbitals are used. Hybrid orbitals are used. A bonding MO is the bond, VAC pair is violated. Actually, unhybridized orbitals are being used in a delocalized MOT because actually hybridization, that is a concept of valence bond theory. So whenever, and the limitation of valence bond theory is that the those hybrid orbitals are actually highly directional. It is not delocalized all over the molecule. So in case of delocalized MOT, we are dealing with unhybridized orbitals are used. Then question number 5, it is saying the photoelectronic spectrum. What I was saying just before that, PES, photoelectronic spectrum of methane has, methane means CH4, right? Uh, CH4. So in one of the lectures, I think Professor Anindya Datta in, I guess, in week 11, the last class, last lecture, you can see last or the penultimate lecture of week 11, he has taught in the class that how this molecular orbital of methane looks like. Where, so methane has been discussed in two ways. One using valence bond theory, that hybridization, sp3 hybridization, and another is through the MOT picture. So both the picture has been uh, means both the theory has been discussed by professor in the lecture. So you can look at that. But in this particular question, whenever we are discussing the photoelectronic spectra, then we are talking about the MOT picture, molecular orbital theory. So, and that is more acceptable than the VVT. Okay. So, what it is saying that from photoelectronic spectrum of methane, two bands are observed, B1 and B2. B1 is lower, B1 has a lower ionization energy, and B2 has a higher ionization energy. What does that mean? So it means that it will require more energy to remove an electron from B2, right? That means B2 is energetically in lower position. So if I draw like this, so your B1 is here and B2 is here. That is why your B1 has a lower ionization energy and B2 has a higher ionization energy. Whenever we draw the this kind of CH4 or this kind of MO, suppose there, so we actually work with a SALC, symmetry adapted linear combination, 4 hydrogen atoms. Actually, these kind of MOs or the SALC concept of SALC is actually available in the there is a rerun course by Professor Datta in NPTEL, symmetry and the group theory. You are welcome to look at the course in the. I think that course is going to be again offered in the upcoming semester. You can take that to understand the symmetry part. But anyway, the carbon and so suppose there are for carbon there is uh, 2s, and so 1s is very energetically down compared to the 4h, and 2s and 2p, this 2px, 2py, 2pz are there, and accordingly that actually these there are four electrons coming from the four cells, and obviously carbon has how many valence electron carbon has actually 4 to 1, it has carbon is 6, so 1 is 2, 2 is 2, 2p2, right? So 2 electrons here and 2 electrons here. So total 8. Actually, you will see that there are two bonding kind of orbital. One with this helps with 2s, and here B1 is actually degenerate. There are three electronic orbitals there. I request you to look at the molecular orbital diagram that is presented by Professor Datta in the lecture. So that is why I mentioned it earlier. So you will see that actually B1 there are actually 1, 2, 3, 6 electrons are there and 2 electrons there in B2. So that is what they want to know, the ratio of areas under the B1 and B2. So in photoelectronic spectrum, you are going to get this kind of things. Suppose obviously in x-axis it is energy and y-axis it is intensity. So suppose you have two peaks like this. Two peaks will have two different intensities, right? And the area under the curves is dependent upon the intensity, right? So suppose B1 has lower ionization energy. Suppose your ionization energy, I energy is increasing this way and intensity obviously that way. So suppose this is due to B1. So I will try to use a different color for that. Suppose B1, the area under the curve is actually then dependent on the height or the intensity, right? Eventually, and suppose this part is blue. Okay, so I will write it here. That is a bad idea. So this is B for B1 and this is for B2. Oh, the intensity will depend how many electrons are there in that orbital that we can remove. So we can remove six electron from B1, so the intensity would be higher for B1, and for B2 there are option two electrons are there. So ultimately what we can see that the ratio of the areas are also going to be 6:2, or we can say 3:1. So that is why it is also going to be 3:2. Second. So, okay. Now with that, actually we are going. So I have also collected a few questions from internet and some online platforms for quantum chemistry. So I thought that this is going to be a last class, so I should solve some numericals, I mean, based on the MCQ type of questions from different competitive exams, or you say a different uh, coaching platforms. I tried to accumulate some questions from online platforms, and here they are. We let us solve a few questions. We have around 25 to 30 questions like this, and let us do one by one so that within 2 hours we'll be able to solve all these questions, and that would be a good end, I hope, to the course. Anyway, uh, so the first question is the highest energy pi molecular orbital for the allyne system is. So there are four pi molecular orbitals are given from the, as you can see, the, the- from the options. The four pi molecular orbitals are given. We have to find out which has the highest energy. So what should we do? Do we need to calculate the energies, or what is the easier way here? The easier way here is to look at how many nodes are there. More the number of nodes, more is the energy. Means suppose there. So in let us calculate the number of nodes first. So in case of question number one, option one, that now what are the number of nodes? How can we, what is a node? Node is a place where the wave function changes its sign. Not only becomes zero, it becomes zero, but after the nodes and before the node, the signs are different. So that is the definition of a node. So your sign should change of the wave function. You see here how many nodes are there. You see there are no nodes. So for here, node is 0. What about the second one? There is one node is there, right? What about this? The third one, actually, there you can see there are two times change in the node are number of nodes is 2. What about this? Here, question number 4, they have also only one number of nodes. It's changed one time, but then remain minus, right? So there is only one. So you will see that in question number 3, or option number 3 has highest number of nodes, and that means that it has a highest energy. So that's how you do it quickly, right? You don't have to think about anything else. You just see how many nodes they have, and as we have solved a few questions, or so this is the concept that the more the number of nodes, the more is energy. Anyway, now let's us move to the next question. Please let me know if you have any doubt in between. Now, question number 2. It is a question from variational theorem. The question is the energy functional form of a trial wave function is given as E of alpha that is equals to alpha square minus 3 alpha whole divided by 6. The variationally optimized energy is what? So actually, the trial wave function is not given, and what they have done is that they have calculated the energy. So they have calculated the energy, and actually this is what we have done earlier also. This is the epsilon, or the functional it is called. That is given alpha square, so alpha square by 3 alpha divided by 6. So one, now for variational theorem, what we need to do, that alpha is the variational parameter. So we need to see that using a trial wave function, this is the energy functional we are getting. So we have to see that for what value of alpha this functional energy functional is 0, or is close to the actual energy. By upper limit theorem, we know that it has to be equals to or greater than the actual energy. So what we do, we take a actually derivative of this functional with respect to the variational parameter, that is alpha here, and we make this to 0. What does this mean? This means there is a break in the slope. What does d of d alpha of the energy functional means? Means that there it defines the slope of this energy functional, right? And when the slope is zero means there is a break in the slope, right? Uh, and that break either could be due to break in the slope means like this kind of situation. Here is a break or here could be a break. So if it is like this, so there is a maxima, right? Maximum. And if this is the case, then there is a minimum. So in for both of the case, your d epsilon or d functional by d alpha is going to be zero. And we are looking at such inflation points. So let us do that. So if we do d of d alpha alpha square minus 3 alpha whole divided by 6 equals to 0. Sorry about that. That equals to 0, then it is 2 alpha minus 3 by 6 is equals to 0, and alpha is 3 by 2. So for alpha 3 by 2, there is a break is going to happen, obviously. And you can also see that d2 energy functional by d alpha 2 is going to be that d of d alpha 2 alpha minus 3 by 6, that is actually a constant, um, 1 over 3. So it doesn't depend on alpha, but it is always going to be a positive one. And whenever this double differentiation is positive, that means you have a minima. So for alpha is equal to 3 by 2, epsilon alpha is equal to 3 by 2, the energy functional or epsilon, whatever you can say, that is actually going to have a minimum, or that is our optimized energy. So we'll put the value here. So 3 by 2 square minus 3 into 3 by 2 divided by 6. We have 9 over 4 minus 9 by 2 divided by 6. Am I doing it correctly? 6 is going to be 3 by 2. So the energy value that we are going to get is minus 9 by 4 into 6, that is 3 by 8 minus 3 by 8. So the second option is correct. So variationally optimized energy is minus 3 by 8. There is obviously some units are there, but it's not given, but we don't have to think about it. So that is how you do a variational theorem problem. You can see that today I have uploaded the previous day's uh, recording session on YouTube, that where we have done a few numerical problems on the variational theorem, where we have given in the question our trial wave function is given, and how we what are the steps are to be taken to get the variationally optimized energy that we have done for two numerical problems. And here also we have done for a simpler problem. I hope the concept is clear. Now let us go to the next question. The question number 3. An unnormalized wave function of hydrogen atom is given by r square. So this is the one of the important problem. Um, so before doing that, let me write down the actual wave function that uh, you are familiar with. So the radial part of the wave function, if you remember, so it is actually not easy to remember, but it is minus n. N is a normalization constant. It is dependent on the primary and the principal and the azimuthal quantum number. And there is something like e to the power minus r by n a naught. A naught is the actually a constant, where and n is the your obviously the principal quantum number. And there another term is going to come, that is r 2r by n a naught to the power l. L is azimuthal quantum number, and then your 12 plus 1, and here n plus l of n a naught, sorry, 2r by n. This part is known as associated Lagrange polynomial. So what I am going to give you is a kind of a trick, you can say. This kind of problem sometimes comes in the CSIR net, that your radial wave function, you don't have to remember all the things. Here you can see that the gist to be taken, that your RNL, the radial wave function, is a function of exponential function of minus r by n a naught, n a naught, and it is also a function of r to the power n. That's what you have need to see. So you always need to see that what is, so suppose in this question, what is the question saying? That an unnormalized wave function is given of a hydrogen atom, and that is your, that is, so that unnormalized wave function is given by the r square e to the power minus r by 3 cos square theta minus 1. This part we don't want right now, but you can see this. So r to the power 2. So, and here you can say that your radial wave function r to the power l terms. So your l is actually 2, right? Now, what about n? You can see your exponential function, exponential minus r by 3. Here you see that it is exponential minus r by 3 a naught, something like that could have been there, right? So your n is 3, that you know. So your n is 3, l is 2. Now, what are the option that could be? See, now there is no phi dependent part, right? So if there was some phi dependent part, then you could have seen, say that ml has some non-zero value. But now, as there are no phi dependent part, that means here m is also 0. So m is also 0. You can see that for l equals to 2, m could have been plus 2, plus 1, 0, minus 1, minus 2. There are 5 options could have been there. But for each of them, uh, except 0, you would have a phi dependent part, but that is not there. So your actually correct answer is this. Okay. Now let us discuss question number 4. The question number 4 says us I'd ask a satisfactory spin wave function for an excited state of helium. Spin wave function, not the overall. What we know from the first of all, electronic configuration for a helium excited state of helium would be one of the state could be 1s1, 2s1, right? Actually, in ground state it is 1s2, but in excite one of the excited state could be 1s1, 2s1. So your electrons are in two different orbitals. One is 1s and another is 2s. So the spatial part you can write the spatial wave function could be written in two kind of system, two linear combination. One is 1s plus 2s. I'm writing it simplifying, and another is no, not like this. So that actually that is not correct. I will write on the things. So electronic configuration is 1s1, 2s1. So the spatial wave function can be two things that 1s1, 2s1, 2s2. The second electron is in 2s, and another option is the second electron is in 1s, and the first electron is in 2s. This is one condition with plus, and another could be 1s1, 2s2 minus 1s2, 2s1. If you see, these are the two options for the spatial wave function. One, so the first one with the plus combination is, you can see that is a symmetric with respect to the exchange operator. If you change 1 with 2, this function, the first one, first linear combination is actually symmetric. And the second one with a minus combination, minus linear combination is anti-symmetric. So this is symmetric with respect to exchange of the electrons, anti-symmetric. Now your quantum six quantum mechanical postulate tells you that electrons are fermions, and those fermions should have their wave function should be at the total wave function should be anti-symmetric with respect to the exchange of the exchange between two particles or two electrons, right? So now your total wave function should have been anti-symmetric, and we know that total wave function means a spatial total wave function is a product of spatial wave function and the spin part. So if and the total have to be anti-symmetric. Okay. So you see your if your spatial part is symmetric, then your spin part have to be anti-symmetric, and there is only one option. The spin could be anti-symmetric, alpha 1 beta 2 minus alpha 2 beta 1. That means that first electron have alpha spin, second electron has beta spin, and uh, another, that means that alpha has second electron has alpha spin, first electron has beta spin. Why we are writing in a linear combination in both spatial part and spin part? Because they are electrons are indistinguishable. We cannot differentiate that which electron is which, right? That is why we are writing it like that. With the negative combination is leading to an antisymmetric thing, and this if we have to pair the symmetric special part with the antisymmetric with this antisymmetric spin part. So one option is this, and the other, when it is antisymmetric, your special part is antisymmetric, then you have actually three cases. You both the spins are alpha, both the spins are beta, and another symmetrical condition. Your first has alpha, second has beta, the positive condition. Your second has alpha, your first has beta. This is another combination. Obviously, the you can judge that it has a 1 by root 2 as a normalization condition. And obviously for these cases also. So you can see that what are the possible spin could be like this, but it cannot be alpha 1 beta 2. It cannot be possible. It could have been alpha 1 beta 1. Sorry, alpha 1 alpha 2. Alpha 2 beta 2. But so 2 and 4th option are incorrect. What about this? So here it is written that both are alpha, both are beta. So this is also not possible. This is overestimation. So now actually the first option is going to correct. See, 1 by root 2, that is alpha 1 beta 2. So your first have, so this is this condition what we are discussing, that this one. Let me highlight this one. I am talking where your spin function is symmetric, and that's why your special part has to be antisymmetric. Anyway, let us see what is the next question. Next question is easy, that for a particle of mass m in a one-dimensional box of length 2l, the energy level corresponding to n is equal to 8. First of all, what is the, suppose there is a particle in a box, what is the energy? We know that for a length of L, that is n square h square divided by 8 m L square. When the box length is L, now here they are saying the both box length is 2L. So let us do that. What we can do, that will become 2L square, right? And they want to know for n is equal to 8. So also we can remove n, and in that place we can 8, right? What we are going to have, so this 8 and this can cut. So 8 h square by 4 m L square. We can also short it down. 2 h square divided by m L square. Do we have some option like that? 2 h square by m L square. See, the fourth option is correct. Okay. Okay then. I hope the concept is clear so far. Till now, do you have any questions?
No, sir.
Okay. Okay. So then let us go to the next set of questions. Actually, these also I have taken from some online platform. So let me acknowledge them at first and then we will start. So the first question is that the eigenfunction is given. So you know what is eigenfunction and what are the operators. So for a eigenvalue equation, when your operator works on that eigenfunction, it gives back your eigenfunction with a eigenvalue. So here your eigenfunction is given. So here let me write it here. Your eigenfunction is 1 divided by pi sine 3.6x. Right? This is your, suppose this is your f of x kind of thing. It is a function. Now your operator is also given. Your operator is minus h not part square. I have a tendency to h square minus h square by 8 pi square m d2 dx square. So this is the operator and this is the function. So it will operate on this and will give me something. So see, 1 over pi is a constant, so we can take it out. So let me first write minus h square 8 pi square m 1 over pi. Then I am going to do d2 dx2 of sine 3.63x. So we have to differentiate twice. So let us do one by one. H square by 8 pi square m 1 by pi. I am keeping it outside. Now d by dx. If I write d by dx once, so already one time it has been done. So that is going to be your cos differentiation. I should for clarity let me erase this. What I am trying to say is here I am doing two time differentiation. So first time differentiation is yielding me cos sine to cos, right? 6 3x x, and obviously 3.63 will come outside once. So 3.63 will be there. I don't know, today my pen this pen is not working properly. 3.63 into this. So this is I should say minus 1, right? So these are all products, or else it will like I am doing a subtraction. But anyway, now one time differentiation is left, but differentiation of cos leads to sine function, but with a negative sign, right? D of dx of cos x is minus sine x. So I am going to have a minus 1. So I will not bother that I have already a minus 1 and a minus 1 I'm going to get. So minus minus will be positive. So I will not bother about that. But the constant term that will eventually come up, that is also going to 3.63. So I'll take a square of that. So these are the constant which were there earlier also, don't change, and your cos function will become sine 3.63x, right? So you will see that you have got back your eigenfunction 1 over pi sine 3.63 3.60x. So this is your eigenfunction. So obviously you are operating operator on some eigenfunction, you are getting back your eigenfunction. So this obviously this is your eigenvalue. Now check out of this 4 which is your eigenvalue. You have to have 8 pi square m in the denominator. You have in b and d, but in d you have a minus 3.63 square. That is not correct. So actually your b option is correct, right? 3.63 square h square by 8 pi square m. So that's how you do it. Okay. Now let us go to the next question. The second question is, for a particle in a 1D box with infinite walls at x is equal to 0 and in the n is equal to 3 state, the probability of finding the electron in the range of, so first of all, this is a particle in a box problem. Okay, the walls are at x is equal to 0 and obviously at n, and what is the wave, so what is the wave function looks like? So psi 3, right? Because n equals to 3. So psi 3x will looks like root over 2 by L sine n is 3. So 3 n pi x by L, right? This is my wave function. Now we have to find the probability of finding the electron in this range 0 to L by 4. So obviously your psi star, the complex conjugate, is also going to be the same, right? Because there are no complex term in the wave function. Hmm? So what is the probability? Probability is the in finding of area. So 0 to L by 4 you have to look at. So you are going to look at psi star, psi dx, 0 to L by 4. Psi star is going to be 2 by L. Will, as a constant, it will come outside with a root 2 by L into root 2 by L is going to be 2 by L, right? And then it is sine square 3 pi x by L. Now we are into our known territory, right? Sine square 3 pi x by L. So you know the trigonometric function, right? That 2 sine square theta going to lead 1 minus cos 2 theta. Okay. Similarly, here we have 2 outside, so I can take it inside. So it is 2 sine square 3 pi x by L. So I can write it out as 0 to L by 4, 1 minus cos 6 pi x by L dx 1 by L. So this is x. So integration of cos 6 pi x of L is going to give me plus sine that thing. So sine 6 pi x by L, and here L by 6 pi will come in, and the limits are from L by 4, 0 to L by 4.
सर स्क्रीन में नहीं दिख रहा है।
आपको पहले भी नहीं दिख रहा था क्या?
नहीं सर, अभी बस 5
ओके
मिनट हो रहा है, नहीं दिख रहा है।
ओके, आई एम वेरी सॉरी. Let me see, let me see. Then me unshare the screen once and then I will share screen. अभी आपको फिर से दिख रहा है?
बस नहीं दिख रहा है।
अच्छा, आप एक बार rejoin करेंगे?
जी सर।
Maybe after the internet connection is not good. Let us see.
जी सर।
Hi. Can you see now?
यस सर।
Okay, okay. Okay, let us again see where we were. So we were solving this integration. So I think you have missed this part, right? So let me
Yes,
discuss
sir.
again. So what we are trying to solve was that the question is that for a particle in 1D box with infinite walls at x is equal to 0 and L obviously in the n is equal to 3 state. So the particle is in n is equal to 3 state. So for that we have written the wave function. So we know that wave function particle in a box, right? Root over 2 by L sine n pi x by L. So in case of n, in place of L, sorry, n, we have written 3. So 3 pi x by L. Now we have to find the probability of that electron in this range, 0 to L by 4. So for that, obviously, we have to do this integration. Integration 0 to L by 4, psi star, psi dx, right? 1D box, probability. So the psi star and psi are probability density, and dx is your, you can say your volume element. So your some density in the volume will lead you to that actual thing, right? Mass kind of thing. That is your, here is your probability. Okay. So right now we are multiplying psi star psi. That is going to be 2 by a sine square 3 pi x by a. And now you can see that 2 sine square theta can be written as 1 minus cos 2 theta. This is this uh, trigonometric function we are using for a very long time, right? That whenever we are seeing some integration of sine square function, we are trying to make it in a 1 minus cos 2 theta, so that the order that 2 sine square integrating 2 sine square theta would be very difficult, but integrating 1 minus cos 2 theta is very easy to do that. That is why we are changing it from 2 sine square theta to 1 minus cos 2 theta. So that's what we have done here. So 1 minus cos 6 pi x by L. So we have taken this 2 inside. So it has become 2 sine square 3 pi x by L. And that can be equated to 1 minus cos 6 pi x by L. Okay. Now it is 1 by L, and integration of 1 dx is going to be x, and integration of cos 6 pi x by L is going to be L by 6 pi sine 6 pi x by L. Now the limits are from 0 to L by 4, because we need to, as per the question, we need to find the electron, the probability of finding the electron in this region, that 0 to L by 4. So let us do that. Now we will put the values. L by 4 minus L by 6 pi sine 6 pi L. In denominator there is a L also, and also a 4 will come, L by 4, right? And then we have this 0, right? So we will place minus 0, and minus minus plus, it will also be 0. So I'm not writing it because it will become sine 0, right? Sine 0 is 0. So if in place of x I put 0, so it will become 0, right? Sine 0. So sine 0 is 0, so I'm not writing anything. So I put it as 0. And also here your L and L are going to cut, and it is going to give you 3 pi by 2, sine 3 pi by 2. So we need to know what is the value of sine 3 by 2. But see, 1 over L is outside there, so we can cut these L's also. So eventually it is 1 by 4 minus 1 by 6 pi sine 3 pi by 2. Okay. So what is the value of sine 3 pi by 2? So that is sine 270 degree. So sine is in the third quadrant, all sine, tan, cos. So it is something in that third quadrant. So obviously it is going to be a negative. So it is, I guess, minus 1. Uh, yes, sine 3 pi by 2 is minus 1. So obviously you are going to get 1 over 4. So minus 1 minus minus it will be plus 1 by 6 pi. So let me see what is the value. I will try to uh, look at the calculator in my phone and so 1 divided by 4 plus 1 divided by something coming as 0.03. Sorry, 0.30303, which is actually close to 1 by 3, right? 1 by 3 is greater than, the options are greater than 1 by 3, exactly 1 by 6, none of the above is correct, and exactly 1 by 3. So we can actually write exactly 1 by 3. Yeah, because you can see that your 1 by 3 is what? 1 by 3 is 0.33. Here we are getting 0.3, so we can write it is at 0. Yeah, as exactly 1 by 3. Okay. So I am actually have to erase this part because the next question is going to come here. Okay. The next question is there that which of the following statement. So did you get the idea what we have done in the last question, that the probability of finding that electron in that region for a particle in a box with n equals to which is there in the n equals to 3 state, their probability is 1 by 3 or 0.0.3, right? And let us go to the next question. Question number 3, which one of the following statement is true about particle in 1D box with infinite wall? So again, this is a question for particle in a 1D box with infinite wall. Which of the following statements are true? The first statement is integral psi 3 square dx is 0 because of wave functions are orthogonal. Then it is said that, achha, let me do one thing. Let me copy this here. Delete all of these things so that. Okay. So I have put it here. So the question number 3. See, which of the following statement is true about the particle in a 1D box with infinite wall? So let us first draw. So you will give me the answer. Huh? Before that, I will draw the all the things. So if I draw the box like this, which is a very bad drawing. So suppose there are 3 states. N equals to 1, n equals to 2, and n equals to 3. Okay. Now, how does this wave function looks like? This is the n equals to 1. This is the n equals psi 2, and psi 3 looks like this, right? So this is your psi 3, this is psi 2, and this is psi 1. All of them are normalized and orthogonal to each other, right? So you tell me out of these 4, which option do you think is not correct? Or which statement is correct? The first one is saying integration of psi 3 square dx is 0 because of these functions are wave functions are orthogonal. Is this a true statement? What do you think? See, psi 3 square means psi 3 star dot psi 3 here, obviously. That is actually a normalized condition. That is not an orthogonal condition. Actually, first of all, the statement is wrong because the psi 3 square dx should have been 1, not 0. So that is not a correct statement. So obviously, that is not correct. What about the second one? That psi 1 integration of psi 1 into psi 3 dx is 0 because these functions are symmetric. Obviously, psi 1 is symmetric and psi 3 is also symmetric. But because of so the the statement is correct, but the reasoning is wrong. So the statement is correct up to this part is correct, but this part is wrong. Okay. What about C? Psi 1 and psi 2 are 0. Integration psi 1, psi 2 are 0 because these wave functions are normalized. Again, the statement is correct, but the reasoning is incorrect. Now look at the fourth statement. That integration psi 1 psi 3 dx is 0 because the wave function is orthogonal. Yes. So statement is also true and reasoning is also true. So both the things have to be true to be a correct statement, right? So this is correct. So did you get the idea what I'm trying to say? So psi 1, psi 2 and psi 3 are individually normalized to each other, right? The psi 1 square, psi 2 square, psi 3 square, their integration all over the space is going to be 1. But when you multiply psi 1 and psi 3 and take the integration all over the space, then it will be 0 because psi 1 and psi 3 are orthogonal. That is a property of this 1D box. Okay. So then let us go to this question number 4. Which of the following is true? So there are 4 sets are given. So these kind of operators are actually known as your commutator relationship. Commutator means your A. So these I will actually give you as a homework. I'll give you the answer, but you have to see what why this. So this means obviously they are operators. Okay, the commutator means this. Okay. Now I will give you the correct answer. This is going to in this case all these commutator relationship what has been shown are correct. But in the rest of the cases it is not. It is your homework to do the thing. Huh? I hope you will be able to do that. I am not doing it for a time restriction, so I do not have that. I have many more questions to solve, but you try to solve it by yourself. I'm giving you the correct answer, but you try to solve it by yourself. Now we'll go to the next question. That consider a quantum mechanical problem where the eigenfunction is a spherical harmonic that is given with L is equal to 1 and ML is equal to 0. Okay, that means here this is given. So this is your n cos theta is your wave function. Now we have to find the normalization constant. So if I have to find the normalization constant, then I have to do a normalization condition, right? Theta phi, it depends both on theta, both on phi. But you can see only cos theta is given, the phi part is missing. So you need to do a integration over this volume element, and that should be equals to 1. So, and it is going to be n cos theta. What about the d tau? D tau here is sine theta d theta d phi. This is spherical polar coordinates. That's why the d tau is different from the usual Cartesian coordinates what we use. So now there are going to be two kind of integral, which is one is based on theta, another is based on phi. So actually, I should write square of them. So n square cos square theta actually. So n square is outside. Cos square theta sin theta d theta, and for phi it is d phi is going to be 1 because this is normalization condition, and your theta can go from 0 to pi and phi can grow from 0 to 2 pi. Due to that, now I should say this is n modulus square because n star dot n. I don't know yet what if n going to be a imaginary or not. So that's why I'm taking a modulus of that. Now I have the integration 0 to pi cos theta sin theta d theta. So what I will do, I will choose cos theta as p. So my if I take a differentiation with respect to theta, then sin theta d theta is going to be my dp. Okay, actually minus dp. D theta of cos theta or this uh, that is minus sin theta. So I will take minus dp on that side. So 0 to pi. Oh, I should not say 0 to pi because now I have changed the variable. So theta can go from 0 to pi. So what about the p is going to be for p? What is the going to be limit? So p is cos theta. So for theta 0 to 0, p is going to be 1 cos 0, and for theta to be pi, it is going to be minus 1. So 1 to minus 1. D square sin theta d theta is minus dp. So I can take this minus outside, right? And d phi is going to be pi 0 to 2 pi equal to 1. So minus n square. Actually, this minus I can actually take like this. I can use that minus sign to revert the limit. Minus, so it was 1 to minus 1. Now I am reverting minus 1 to 1 p square dp into 2 pi. From this side, we are going to get 2 pi, and it would be p cubed by 3, right? N square p cubed by 3, and the limits are from minus 1 to 1, and obviously 2 pi is already there. So, and that is equal to 1. And p cubed by 3 1 by 1, that way is what? Let me write it here. 2 pi n square 1 over 3 plus 1 over 3 is equal to 1. So we have 4 pi by 3 n square is equal to 1. We have n as 3 by 4 pi root over. See, your n normalization constant is root over 3 by 4 pi. So that is a very easy problem. Just you need to find the normalization condition, you need to put that wave function into your normalization condition, your bond condition, bond max, that bond condition that you are going to get. The probability of finding that particle all over the space is going to be 1. Okay. Now let us solve the next question. That is question number 8 actually. Consider all the following statements, and out of which we need to find out which are true. So question number one, sorry, the statement number 1 says all eigenvalues are real. See, eigenvalues are going to be real if my operator is Hermitian. So obviously all quantum mechanical operators are Hermitian. Okay. So my eigenvalue have to be real. So statement number one is correct. Now let's see about the statement two. So I will mark it that this is correct. Now the statement number two, eigenfunction of Hamiltonian operators are orthogonal to each other. Hamiltonian eigenfunctions of Hamiltonian operators. Hamiltonians means the energy operator. So obviously for each, so this is also true. Just now we have done for a the same thing we have done for that particle in 1D box, right? For which we got psi 1, psi 2, psi 3, and we told that psi 1 and psi 2, who if you multiply and integrate all over this space, that is going to be 0 because psi 1 and psi 3 are uh, orthogonal. Actually, their Hamiltonian operator is same, but the eigenfunctions are actually different. So those eigenfunctions are actually orthogonal to each other, and that is true for all quantum mechanical systems. So statement 2 is also correct. What about statement 3? The two Hermitian operator A and B, if they commute, A and B are Hermitian. If A and B are Hermitian separately, then AB is also Hermitian. So see what they are saying, that A, B, they commute. They commute means that is equal to 0. And that is A, B, minus B, that is 0. And also they are saying A and B are Hermitian. That means A dagger is A, means A is Hermitian. B dagger is B, means B is Hermitian. What about AB dagger? Is AB Hermitian? So to AB Hermitian, this means B dagger, A dagger. So this is actually how it been written. Not A dagger, B, not AB whole dagger is not A dagger, B dagger. It is B will come first and then A will come. And you know B dagger is B, we know, because B is Hermitian, right? A is Hermitian, so A dagger is A. And from the commutation relationship, we know that BA is AB. So we get that AB dagger is AB. So AB is also Hermitian. So this 3 is also correct. Now, statement number 4, the eigenvalue of anti-Hermitians are either purely imaginary or equal to 0. To be honest, at this point of time, I don't have the idea. I will actually look into this statement and I will tell you later. But the first three statements are correct. You have to look for the fourth one. So that's why I am not solving it entirely. You have to find it out that, and obviously after that I will, in the discussion session, I will write it down that what about the statement number 4. So the eigenvalue of anti-Hermitians are purely imaginary or equal to 0. At this point of time, to be honest, I don't have the idea. I'll look into it and I will tell you. Okay. Now let us go to the next question. The next question is, we have, there is a free particle of mass m is moving in one dimension. Then we have to see what is the commutation of this Hamiltonian and the x. Actually, this should not be momentum operator. The question should have been position. X is position operator, right? So let us do that. H is nothing for a free particle. It is h cut square by 2m d2 by dx square, right? And it is x. Suppose it is going to operate on some f of x. Yeah. So a commutation is how it will work. It is minus h cut square by 2m d2 dx square. First it will work, x will work on f of x, so it will look like this. Okay. Now your minus minus plus x is going to be on the left hand side, and now h cut square by 2m d2 dx square of f of x. Okay. From the first two, what we are going to get? Minus h cut square by 2m. Obviously, we are going to do twice d of dx. So first we are going to get f of x. Second we are going to get x f dash x. And from this side we have x cut square by 2m f double prime x, which is double derivative, right? Now from this side we are going to have minus h cut square by 2m d dx of f of x is actually, let me write f dash x, and this is minus h cut square by 2m. Again we are going to have two terms, that is one is going to be f dash x and another is going to be minus h cut square by 2m x into f double dash x, and this part is already there, x is cut square by 2m f double dash x. So you will see that these are the things that is going to cancel each other. The first two are going to cancel each other, and the first and the second are the same. Third and the fourth are cancel each other, and first and second are the same. So actually we are left with minus 2h square by 2m f dash x. So I can write it also as d of dx f of x, right? We're left with this 2 and 2 will also cut each other. Okay. Now that's not all. If we look at the answer, that minus h cut square by m d of dx of f of x, obviously we cannot see anything here, right? Any answer A, B, C, D, none of them looks like this. So we have to do something so that it becomes like our answer what is given in the question. So h cut square is nothing but h square by 4 pi square m, because h cut is h by 2 pi, right? D by dx f of x. Now you can see it is h square 4 pi square by m. Now if I have to write it in terms of the, if I need to see in all the option, they have introduced that momentum operator P. What is a momentum operator? That is minus I h cut d by d. What do we have it here? We have minus, we don't have I, we have H. Actually, to be honest, let us stay at this part from now. This part let me remove. So we have H, we don't have I, we have d by dx. So if I have to introduce this, how can I do? So obviously I will place one I here, one of the each I will take, another each is left. If I have to introduce I in the numerator, then I have to multiply in the denominator also. I'm keeping as it is, d by dx, f of x. So these are the tricks what we am doing. So you have minus h cut over im ih d by dx of f of x, which is nothing but this time is p. And so I'm taking minus here and plus here. So this I in the denominator can be taken into the as minus I also. If you multiply I again in the numerator, you have to multiply in the denominator, and in denominator you are going to get minus 1. So minus I. Now each part I will write in terms of h uh, over 2 pi m, and I will write p operator, okay, and f of x. So I can see, so this was my operator, right? The commutator, this was my operator. So they want to know what is h and x means, what this commutator is equivalent to. So this is equivalent to minus I h divided by 2 pi p hat by m. F of x is a eigenfunction that upon which we have operated the commutator and we have get back the f of x. Okay. So your question number, actually option number 1 is correct. Okay. Now let us solve the next problem. Next problem is on which in a one-dimensional box again, but the length is 2b. Oh, no problem. We know what length 2b means, right? So the energy will be n square h square divided by 8 m 2b square. Okay. And what is the n? N is third excited state. Third excited state means n is 4. Okay. Your ground state is 1. First excited state is n equals to 2. So third excited state is n equals to 4. So don't get confused about this. It is something like third floor means 4-story building. The building has 3 floors. Sorry, the third floor in the elevator, when you mark in 3, you are going actually to the fourth story of that building. So something like that. So it is third excited state means n equals to 4. 8 into 4. Sorry. 4 m square. So we have 4 square as, okay. So you, this is the energy of your 16 a square by 32 mb square. This is the energy of your third excited state. Now the electron is coming to the ground state. So the energy of the ground state is obviously h square by 32 mb square, because it's 1 square, right? So now what is the energy will be then? Energy will be in a delta E is E4 minus E1, that is 15h square divided by 32 mb square. So the first option is correct. Now let us go to the second question. The second question is that the also about particle in a box, but this is a little different. For previous questions, we have assumed that the walls are at 0 and L position. But we have also solved the problem like this, that for a particle in a box for which the suppose what I'm trying to say. Let me write it here. So for a particle in a box for which the walls are at x is equal to 0 to L, so their psi n is root over 2 by L sine n pi x by L. Okay, but when the same thing, same box, we'll assume it is from uh, minus L to plus L. Obviously, the box length has doubled. Uh, I should account for that also, else from minus L to plus L. Sorry about this. Think of this as straight line. So then your psi of n can be two things. So 1 by L sine function n pi x by L when n is even. So we have solved this problem in one of the discussion session. I will urge you to look at, I guess, lecture number, so discussion session 4 or 5th. It is there. Or cos function n pi x by L when n is odd. So see, it is in the second excited state. So can you tell me what is the n? Second excited state means which? N equals to what? Those who are listening, can you tell me second excited state means here n equals to what? We have just discussed in the previous question, right? What does the second excited state refer to? Anyone? Okay. The second excited state is the n equals to 3, right? So your n is 3, that means n is odd. So your and if I have to minus L to plus L, it would have been 1 over L cos 3 pi x by L. Sorry, it would have been 2L. Yeah, I'm sorry about that. And what else? The another thing is that here it is from minus L by 2 to plus L by 2. So you can replace this L by L by 2. So then your and L is L by 2. So it is going to become 2 by L cos 3 pi x by L. So actually the correct answer is A. Root 2 over L 3 pi x by L. Okay. Now let us move to the question number next 13. So that is your commutator. So this commutator is given that what are the values are going to be. So the first one is very easy actually. This so this is Lx Ly is actually minus I h cut Lz. Okay. So so in option number one it is there. Option number two it is plus, so it cannot be. Option number D, it is also plus, so it cannot be. So you can see it is minus I. It can also be written as minus IH over 2 pi LZ, or also minus H by 2 pi I. Actually, it is not minus. I'm sorry about that. Now the minus will be there. Minus H by 2 pi I LZ. So these are the variation that it can have. And what about Lx comma Ly? Sorry, not Ly but Y. For that, I need a blank page. Let me have that. How can I do my page? Here I will try to do the Lx and Y. And we have to operate it on some f of x, right? And not f of x. I should not say that. It should have been a function of x, y, z, or. So better to write it as psi, which is a x, y, z function of all. Now Lx is what? Lx is y ez minus z dy. In other terms, is minus ih cross y del by del z minus z del by del y. Okay, so that means we have the commutator between minus ih cut y del by del z del by del y and y over psi. So what we are going to get here? Minus ih y del over del z y into psi minus z del by del y into psi. Then we are going to have the opposite. Then it is minus of minus, so it will be plus y into I plus y del psi of del z minus z into del psi over del y. And what do we have here? We have minus ih cut so y is it's not depend on z, right? So it would be y square, but psi is dependent on z. So y square, it will be del psi by del z. What about the next? Next, y psi, that is a both a function of y. So it would be interesting. So first, it would be del y by del y, which is obviously 1, and psi is there. And then we have del z zy del psi by del y. Now what do we have outside? We have plus ih part y square del psi by del z, right? And we have minus ih part yz del psi by del y. So if I remove this bracket, then I need to multiply this ih part minus ih part to everything. That will become plus ih part, and you can see this plus ih y square d inside this and this cancel out, and yz zy this is going to cancel out. So we are left with minus, we are actually left with only one term, that is plus I h cut z psi. So obviously, which is, so your lx comma y over psi gives you to I h cut z psi. So this is your eigenvalue, you can say. So I h z. You see your third option is correct. So you look at this much carefully by yourself. You will see that what we have done just right now. Okay. Now let us solve the next set of problems. That the wave functions for a quantum mechanical particle in a one-dimensional box of length a is given by something this psi, and the value of a for the box we have to determine. So let us do that here. Psi is a sine 2 pi x prime. So you know what a is, right? A is going to be root over 2 by L. L is, and that is a sine function, right? So your A is 2 over 100 nanometer minus half. So root over 1 over 50 nanometer minus half. Let us see if we can finish this. Let's calculate it. 1 divided by 50 to the power 0.5. It gives us to be 0.141. So this is the correct answer. What about the next set of question that if psi n lm are the eigenfunctions of the operator this, then what is going to be eigenvalue? So we know that Lz square is Lx square plus Ly square plus Lz square. So we can write this Lx square plus Ly square in terms of, sorry, my bad, should not be L square, L square, right? Total angular momentum square minus this component square, right? Lz square. Now we actually know this very good, right? The eigenfunctions when it operates on psi NLM, what kind of um, eigenvalue does it generate? So instead of directly looking at Lx square plus Ly square, what we have done when it works on psi NLM, we are looking at L square minus Lz square psi NLM. So L square when it operates on psi NLM, it is going to generate L into L plus 1, right? H cut square. And when LZ operates on that, it operates. LZ operates when, then it operates MH. So when LZ square operates, then M square plus H cut square. And then obviously you're going to get back your psi NLM eigenfunction. Obviously this is your D is going to be the correct answer, the eigenvalue of Lx square plus Ly square. On the next question, question number 17. A particle is moving on a one dimension between x is equal to a to x is equal to b. The potential energy is such that the particle cannot be outside this limit and wave function is given psi is equal to a by x. So your psi is a by x. You need to find average value of x. Average value of x is given by psi x psi in the denominator. You don't know if it is normalized or not, so you have to make it normalized, and it is from a to b with a by x multiplied by x, a by x, right? Dx divided by a to b, a by x to a by x dx. So in the numerator we have a to b, a square outside, we have 1 over x dx. Here also we have a square outside, a to b, 1 by x square dx. What does that? A square are cancelled out. 1 over x is ln x with 0 under x. And 1 over x square is x to the power minus 2. That leads to actually x to the power minus 3 divided by minus 3 a to b. So it is ln b minus ln a, which is nothing but ln b by a, but I will write in the next step. I will not do a step jump. So it will be a minus 3. Actually, it will not be a step jump. B minus 3 by minus 3, then minus plus Oh, I have made a mistake. I'm really sorry about that. So the integration of x to the power minus 3 dx or x square minus, so it would have been x minus 2 plus 1 divided by minus 2 plus 1 that is actually x to the power minus 1 by minus 1. I'm going to minus 3. Mm, it will be to the power minus 1 divided by minus 1 to the minus 1 divided by minus 1, but minus minus plus 1. That is ln b by a divided by 1 by a 1 by b, that is again ln b by a, and there it is going to be b minus a. So then we can also write ab by b minus a ln b by a. This is the correct answer. Okay, now let us go to option number 20. For question number 20, the probability of finding the electron between 0 to 2 alpha to a0 of 1s orbital. So 1s orbital radial wave function is given. So this is just you need to do that integration, right? Integration 0 to 2n0 4 by a0 cube e to the power minus 2r by 0. So the r square should also come because of the d tau, right? R square dr now 0 to pi sine theta d theta and 0 to 2 pi d phi. Okay. This will come. So eventually this is going to lead you to 4 pi. 4 pi is a constant, and you have outside 4 by n cube, and what else you are going to have 0 to 2a naught e to the power minus 2r by a naught r squared dr. So this is actually a standard integral 0 to actually infinity. That actually gives you minus. So I'll just share it with you. Alpha. No, this is not that one. I'm still in previous one, but yes. I can do it outside that 2 by r square. We have to do integration by parts obviously. So for that we have r square e to the power minus 2 by r dr, then minus 2r e to the power minus 2 by n r dr d r square, and this is going to be minus a0 by 2 to the power minus 2 r, and this is going to be 2r multiplied by minus a0 by 2 to the power minus 2 by naught r dr. Minus plus a naught. We have r e to the power minus 2 by a r dr. Now r e to the power minus 2 a naught r dr. That also we need to do once more. Right? And then we are going to have minus plus a0 by 2. I'll take it outside. We will be left with 2 by a0 r dr. Actually, it is very lengthy, but 2 by a0 r. And from this side, we are left with another integration, right? That we can do. It will come to be square by 4, right? This term. So minus a0 by 2 will again come, so that will multiply with this, right? So a0 by 4, uh, a to the power minus 2 by a0, a0 by 4, e to the power minus 2 by a0. I hope I'm doing it correctly. So I'm putting the value here, minus a0 by 2 r square e to the power minus 2 by a naught r. Then it would be minus a0 is already there, and I'm putting the whatever we got from the upper integral to this part, a0 square r by 2 e to the power minus 2 by a naught r, and already minus is there, so again it would be minus. This time it would be a0 cube by 4 minus 2 by a naught R. I think I have made it complicated. Anyway, it's very complicated. So let me also have this 0 to 2 A naught. So then I'm going to have this 0 to 2 A naught. So maybe I can have a blank page on the next slide. And write it there. So what I'm going to do is I'm going to write whatever I'm getting from here. 2A0 I'm putting in place of R square, right? So let me do that. Equal to I have minus A0 by 2 R square. In place of R square, I'm putting 2A0 square e to the power minus 2A0 e to the power minus 2 by A0 into 2A0. Okay, then minus A0 square by into R. R is 2A0 divided by 2 e to the power minus 2 by A0 into 2A0 minus A0 cube by 4, A0 cube by 4 e to the power minus 2 by A0 into 2A0. Okay, now I have to put R is equal to 0. So obviously I will not do it for this. When not do it for this means this R square term, whatever is there, that is going to be 0. So then it is minus minus plus 0. I told you. And then minus minus plus again. So that is also going to be 0 because only that R is there. So I am putting 0 in places of R now. So that leads to 0, and whatever this term will be 0. At A0 by A0 cubed by 4 e to the power, it would be 0. Now let's see what did we get from here ultimately. So we need to cut a few things, right? Okay. A naught is cutting from all the places. Okay. What about here? Here we have minus A naught by 2 in 4 A naught square and e to the power minus 4. Then from here we have obviously e to the power minus 4 we have. What about this term? We have 2 A naught cube by 2. So that 2 and 2 are going to cut. Obviously this is 4, so these 2 and 2 are going to cut. And then what do we have here? A naught cube by 4 e to the power minus 4 is there, and here it is only A naught cube by 4. So it is first is 2 A naught cube minus 2 A naught cube. So I place A naught to the power minus 4 here, and this is only term with the A naught cube term will not be there, e to the power minus 4. Then we have a naught cube again from here, and we have a naught cube by 4 in. To be honest, I am not sure if I am making it correct. A naught cube e to the, so suppose if I am taking a naught cube outside, e to the power minus 4 plus cube by 4. So I can erase a naught cube here. So minus 3 minus 4 is minus, you are minus 13 by 4 a naught cube e to the power minus 4 plus a naught cube by 4. So this is the finding the probability. Oh, 1 is computed. Okay. But this a naught cube is actually a constant, right? And we don't know the exact value. So actually we know 0.52, but can we put that well here? I'm not sure about that. So, oh my God, we have done so many things, and now I'm coming to that if we have to go from 0 to 2 a naught, then a naught will be a, anyway, a naught will be yeah, a constant. So we don't know the value of that. So no meaning of going ahead, right? Because we don't know the value of a naught, so we cannot get any integer value or something like this from here. So obviously e to the power minus 4 is going to be very, very small value in comparison to a cube by 4. So let's not go ahead with this. You try to solve it by yourself once, but you got the gist what we are trying to do, right? Let us go to the next question. Actually, we have 4 more questions to solve. It's already over 9. So, but as this is the last day, so we can actually do a little more, right? So the for the particle in a box problem 0 to n, the value of x cube would be 1. So let us do that. X cube for a particle in a box, right? 0 to L. So it would be 2 by L. It would be uh, root 2 by L. I have already taken it out. Sine. So it would be integral of 0 to L sine square uh, n pi x by L n pi x by L x cube uh, dx. So you have to work it out by yourself that what are the value you are getting, right? So it is also going to be some lengthy thing, but don't worry about this. So, and in denominator, you don't have to think about this because it is already wave function is already normalized. Okay. So I'm just, as the time already passed, so I am giving you the how to do, how you can do it. I'm just giving you the hint and you can do it yourself. I'll be sharing this PDF and these slides with you. Okay. So another question is that question number 23. This is also for a one-dimensional infinite well, but this is from minus a to plus a, and V of x, the potential will be infinity outside the box. And it is saying that the electron will go from n is equal to 4 to n is equal to 2. So you need to, and the frequency of the emitted photon is in hertz. So try to find it now in joules. How can you do that? You can multiply it your h, right? H new, so that you can get it in the so new is given. So for energy you can multiply it with the Planck constant, and here you know that the value actually for energy from minus a to a, so your box length is 2a, so the energy is going to be n square h square by 8m 2x square 2a square. So now you have to take n once as 4 square minus 2 square 8m 2a square. That is equals to your Planck constant into your this new that is given. Harj is nothing but second inverse 3.43 into 10 to the 14. Now if you do that 16 minus 2, that is 12 a square by 8 am into 4 a square is h into that new value, that 3.43 into 10 to the power 14 Harj. Harj is second inverse, obviously you can cross this h once. So you you have 12h. Actually, you can multiply this with 3. So you have 3h by 8m a square is 3.43 into 10 to the power 14 second inverse. We put the value of h, and m is nothing but 9.11 for electron, right? 9.1 into 10 to the power minus 31 kilograms. So from there you have an expression for a square, and obviously take a square root of that. So you will get the value of a. But you need to find the box of the wheel. So that box of the wheel is actually going to be 2a. Don't forget, because the box is from minus a to a. So you will eventually get a, but you need to find 2a. And then, so the width is actually 2a for this problem. Here the boundaries are at minus a and plus a. If the boundaries would have been at 0 and a, then your width would have been a. Okay, so you need to get the value of 2a. I hope you will be able to solve that. And what about the next question? The quantum mechanical probability of finding the particle in one-dimensional box in middle of middle third of the box of the fast excited state. Obviously, fast excited state is here psi 2, right? Which is root over 2 by L sine 2 pi x by L, right? Now, for what is that? Middle third is what? 1/3 to 2/3. So that is middle third. So in your box, if you see 0 to L, so you have L by 3, you have 2L by 3, and then you have 3L by 3, which is it. It's actually 1 by 3, not 3. 2L by 3. And you are going to have your psi 2 star psi 2 means. You need to calculate this and see what are the values you are getting. Okay, that is your probability. Now, the last question actually here, the three real wave functions psi 1, psi 2, psi 3 are normalized and orthogonal. So the what is the normalization constant of the z wave function? So obviously if z is normalized, so if z is normalized, then z star z, or we can say if we take a bracket notation, then it is going to be 1. What about that? So we are going to have psi 1 minus 1 over root 2 psi 2 minus a plus root 3 by root 2 root 3 by 2 psi 3. Okay. On this side it will be same minus 1 by 2 psi 2 plus 3 by 2 psi 3. If z is normalized, then you are going to get this. And it is given that your psi 1 is normalized, psi 2 is normalized, psi 3 is normalized. And also they are orthogonal to each other. Psi I, psi j is 0 when I not equals to j, right? And I and j can be 1, 2, 3. Okay. So from there we can see the cross terms are going to be 0. So that's a good thing. And uh, 1 over root 2 is going to be 1 minus minus it will be plus. Now it is psi 2. We are not even bothering about the cross terms because we know the cross terms are going to be 0, 3 by 2 psi 3, and we told you that they are normalized. So this is 1. Okay, so we have not thought about the normalization constant. So we need to have a normalization constant also. Sorry for that. Suppose z is n into psi 1 minus 1 by root 2 psi 2 plus root 3 by 2 psi 3. So you where 1 modular square is going to come 1 plus 1 by 2 plus 3 by 2 is 1. 3 by 2, 3 by 2. Who is your 3? So your n square is actually 1 by 3. And n is 1 over root. We have the option? Yes. So your option A is the correct answer. Okay. So with that, actually, we have come to an end of this course. I hope today actually we have exceeded the normal 2 hour session to actually 2.5 hour session, but it is actually good that we have solved so many numerical problems and which would be very beneficial for, I hope it would be beneficial for you in for the question solving part at least for your assignment solving, not the assignment so you have already solved, but for the examination part. So I hope the session was beneficial to you, and with that actually I'm going to close today's session. I thank you very much for joining the session and participating and interacting. I hope you have no doubts. If you have any doubt, you can also write it to the obviously to the discussion forum. But do you have any doubt so far, Yogita?
No, sir.
Okay, thank you very much. Then we are going to stop to this session. Thank you very much for joining.
Okay, sir.